My name is Jim Entz. I am Professor of Art here at Porterville College and the coordinator of CHAP. The Porterville College Cultural and Historical Awareness Program, CHAP, was organized in 2002 to enhance students' awareness of important aspects of our society to which they may previously have had little or no exposure. A theme is chosen by CHAP members each school year. This year the theme is the Anthropocene. Events such as this with a guest speaker or speakers are offered throughout the year free and open to the public. And about our co-sponsor, Puente at Porterville College, their mission, Puente's mission, is to increase the number of educationally underrepresented students who enroll in four-year colleges and universities, who earn degrees and return to their communities as leaders and mentors to future generations. Puente is open to all students. Now, if you please take a moment and silence your cell phones, and proof of attendance tickets, or some, I have them, will be handed out at the door there. If, you know, in some classes, extra credits available and so on. So if you want one of those tickets, I'll be there handing them out after the performance, after the event. This evening's CHAP event, co-sponsored by Puente, is on Why Measuring Methane Matters by Dr. Isis Frausto Vincencio. Dr. Isis Frausto Vincencio, am I close enough? Okay. Is an air pollution specialist at the California Air Resources Board, focused on understanding and mitigating methane emissions using remote sensing techniques. She was born in Visalia, California, and is the daughter of immigrant parents from Zacatecas, Mexico. Isis graduated from Strathmore High School and attended the College of the Sequoias before transferring to the University of California, Los Angeles, where she obtained a BS in chemistry with a minor in atmospheric sciences. Following her interest in studying greenhouse gases, she obtained a PhD in environmental sciences at the University of California, Riverside. Her dissertation work centered on quantifying methane emissions from dairy farms and wildfires in the San Joaquin Valley using ground-based solar spectroscopy. Now please welcome Dr. Isis Frausto Vincencio. Thank you.
Hello everyone, thank you for that wonderful introduction, and thank you to CHAP and Puente for co-sponsoring today's talk. So as mentioned, I study methane and I have been for about 10 years. And it's one of my favorite topics to talk about. So let's get started. The title of my talk is Why Measuring Methane Matters. So the outline of my talk today, I will first talk about my educational journey, how I went from community college to PhD. Then I'll discuss my PhD research that was focused on quantifying methane emissions using ground-based solar spectroscopy. And then I'll end the talk with what I do now as a scientist focused on mitigating methane using remote sensing observations. So the beginning of my education goes far back, and as mentioned, I'm daughter of Mexican immigrants from Zacatecas, Mexico. As many of our parents do, they moved to different countries, different states, looking for a better life for themselves and their family. So for us, that meant moving to different states. We lived in Indiana, and then we also lived in Mexico for a while. So most of my middle school and high school education was in Mexico, in Tabasco, Zacatecas, which is, there's a picture at the bottom left corner of a small town nestled between mountains in central Mexico. And then in middle school, what I really excelled at was math and science, even though there was so much change in my life from moving countries and different languages. What really stuck with me was mathematics and science. And during middle school, I read about Dr. Mario Molina, which was the first Mexican to win the Nobel Prize for his discoveries of the chemical reactions that were causing the ozone hole over Antarctica. So in 2010, things got really dangerous in Mexico, and my parents decided it was time to move back to the US. And by that time, I was in almost my last semester of high school. So I always dreamed of going to university and coming back to the US and going to an American university. But by the time we came back, it was too late to apply universities. But I made it to Strathmore High School. And they were grateful enough to receive my credits from Mexico High School, but I also had to attend adult school in the evenings in order to graduate. So I graduated in 2011. And then the counselors helped me enroll into community college. I actually enrolled in PC as well as COS, but my parents moved to Exeter and it was closer for me to attend COS. So there I spent 3 years, but it was a pivotal moment for me as a student. I was new to the education system in the US here, and here I met like-minded individuals. I met students who were also interested in science and transferring to a big university. I'm the first one to go to college in my family, so my parents couldn't really help me navigate the educational system. So I met mentors. I was part of MESA and other programs. So if you're part of Puente, that's a huge resource, and stay involved. From MESA, I learned about conferences, internships, and scholarships. I come from a low-income background, so there was no way I was going to finance my education without loans or financial aid. But scholarships helped me get a full ride to UCLA, as well as doing internships. So I really urge you to get involved during the summers, pick up an internship, do summer research, and really figure out what you want to do, and it'll help you get a job after you graduate. As well as if there's any conferences you can attend, it'll help you network and expand those who you can ask for letters of recommendation, and that's really helpful for scholarships. So during my time at community college, I discovered what I wanted to do. As I mentioned, I was always inspired by atmospheric chemistry, so it really cemented that I wanted to study chemistry. So I obtained my AS chemistry, and I gained confidence in myself to dream big. So I applied to a scholarship called the Jack King Cook, and that was what provided me a full ride to UCLA, as well as obtaining a scholarship from NASA, the guaranteed summer internships, at the NASA Jet Propulsion Lab in Pasadena, where I spent 3 summers doing research. And here's a picture with my parents, and we're at, behind us is a spacecraft that was being built that got sent to Mars. So it was a really cool time, and just coming from community college, so definitely dream big. And at UCLA, I spent 3 years, then I obtained my BS in chemistry and a minor in atmospheric sciences. So during my time there, I was involved in research, and that helped me get to my PhD. But during my time as an intern at the NASA Jet Propulsion Lab, Dr. Francesca Hopkins was my advisor there, and I followed her to UCR to keep studying methane. So when I was at JPL, I helped develop a spatial database of potentially methane-emitting infrastructure in Los Angeles megacity. That was when I learned how important methane was, and I wanted to keep studying it during my PhD. So just last year, I graduated from UCR. And so now let's get started with our discussion on quantifying methane emissions using ground-based solar spectroscopy. So this was part of my PhD research. But to really understand greenhouse gases, we need to talk about first of the Earth's atmosphere. So the major constituent of the atmosphere is nitrogen at 78%, followed by oxygen at 21%. Then we have the trace gases that compose less than 1% of the atmosphere, and we have non-reactive species like argon. Then we have species like carbon dioxide, methane, and nitrous oxide. But someone like myself, an atmospheric scientist, we like to classify these species based on their effect on either the climate or human health. So these are known as the greenhouse gases because they have the ability to trap heat. Then we have species like nitrogen dioxide, carbon monoxide, and benzene, and these can have a negative impact on human health or even vegetation. So these are known as air pollutants. And before we talk about greenhouse gases, we also need to understand the greenhouse effect. So the greenhouse effect is a phenomenon caused by gases naturally present in the atmosphere. In simple terms, as sunlight travels through the atmosphere, or also known as shortwave radiation, it reaches the Earth's surface, it warms up, and then radiates back as infrared or long-wave radiation. And there are gases that are naturally present in the atmosphere, known as the greenhouse gases, that can trap and absorb heat. And these re-emit back in all directions. Some of it does escape to space, but some of it gets redirected back to the surface. So this isn't necessarily a bad thing. It's actually what keeps our planet at a livable temperature. But the problem is when we release too many of these gases, then we're trapping too much heat, and it can cause a rise in temperature, also known as global warming, and a change in climate. Okay, so why methane? I've mentioned CO2, I mentioned N2O as well. Well, methane is the second most abundant greenhouse gas after CO2. It's also very potent. It's 86 times more potent than CO2, and it has an atmospheric lifetime of 10 years. So if we compare that to CO2, CO2 in the atmosphere lasts 100 years. So if we reduce methane today, we'll see the impacts in 10 years. Compared to CO2, we see the impacts in 100 years. So it's methane is known for being a short-term solution for climate change mitigation. And also, methane levels have increased by 150% since the pre-industrial era. So the pre-industrial era is the year 1750, and we can see that concentrations were between 600 and 800, but it just shot up significantly in 1750, and levels continue to rise. So the largest source of methane in California is agriculture, specifically manure management and enteric fermentation, and together they make up more than 50% of the state's budget. And manure management, specifically in the San Joaquin Valley, is due to the wet manure management practice, where dairy farmers wash their feedlots, and then this water with waste ends up in manure lagoons. And it creates the perfect anaerobic conditions for bacteria to break down the organics and release methane. And then we have enteric fermentation, which is a natural process that happens in the cow's gut. Bacteria breaks down the organics, and then the gas is released through the front and through the back. Then we have landfills at 22%, followed by oil and gas extraction at 14%. And then we have wastewater treatment that contributes 3% to the state budget. So in California, we have passed laws to reduce greenhouse gases, and starting with Assembly Bill 32 in 2006, and that called for the reduction of greenhouse gases down to 1990 levels by 2020, and that was met. And now we're committed to reducing our greenhouse gas levels 40% between 1990 levels by 2030. Then there's a 2050 target, which calls for the reduction of 80% below 1990 levels. And then we have Senate Bill 1383 that calls for the specific reduction of methane from dairy livestock, landfills, and fugitive emissions of oil and gas. So as we mentioned, those are the top 3 sources in California. So it's great that we want to reduce it, but how do you keep track of it? Well, you need to measure it in the atmosphere, and there's different techniques commercially available to do that, but it just depends on the source, it depends on your science question. So if you're interested at more of the individual source, maybe a process space where second to second is important, then possibly a handheld instrument or a mobile lab sampling would be best. If you're interested at this second to day temporal scale, possibly regional scale, then aircraft sampling might be best. And then we have longer temporal scales of yearly at global scales, and possibly a satellite would be best if that's your science question. And then we have a sweet spot in the middle with solar spectrometer networks that are able to measure at a regional scale and study intra-annual variability. So now let's get into the meat of why methane is important from dairy farms. So in the state of California, we have over 1,000 dairy farms, and they're located throughout the state, but the majority of dairy farms are located in the San Joaquin Valley. On this map, highlighted in gray is the San Joaquin Valley, and you can see the amount of dairy farms that we have here. And as a scientist, what we're really interested in is quantifying the magnitude and any seasonal variability, but that is highly uncertain. There have been a couple of studies that point that out. As well as emission factors that are used to calculate these large-scale state inventories. Those do not consider any seasonality or changes throughout the year. So zooming into what happens throughout the year is very important. So we can update those emission factors or make any corrections. So I'm going to go through the basic principle of solar column measurements, which is the instrument that I used. And this instrument uses the sun as a light source. There's a solar tracker that is basically a camera, and it helps the mirrors rotate and follow the sun as it moves throughout the sky during the day. Then we have a movable mirror and a fixed mirror. So the movable mirror acts as an interferometer. So there's a beam splitter that splits the light in two, and the movable mirror reflects it back and creates interference pattern. So this is what it looks like, and it doesn't really mean anything if you just look at it. There's nothing you can understand. So it needs to go through some retrieval algorithms, and we call it I to S, so ergon to spectrum. And this, the spectrum is better to understand because these greenhouse gases, they observe at a certain wavelength. So using a fitting algorithm, then we can extract the column number density. And then using some conversions, we can get a column average dry air mole fraction, which is denoted as an X. So this instrument measures anything along the path from the surface and the top of the atmosphere. So for our measurement technique, as I mentioned, we use the solar spectrometer. It's also known as the EM27 sun. And these instruments are about 40 pounds. You can carry them, take them out to the field. They're very compact, stable, and there's been previous studies that have used them in the field. So the way we did it is we calculated enhancement. So you place one upwind, which is measuring a clean background. And as the wind traverses over these dairy farms, then it carries these species over the downwind station. So now you can do a simple subtraction of downwind minus upwind to calculate an enhancement of methane. So for our study area, we wanted to select a cluster, so a group of dairy farms. And if you see on this map, there's a lot of dairies throughout the San Joaquin Valley, and it was hard to pick a location that had a clean background. So we ended up picking our study site north of Visalia because we can measure a relatively clean background. So it's more of a local background to the San Joaquin Valley. And historically, winds are from the northwest. The wind is driven by wind patterns from the Bay Area, and then they come in the northwest direction. So in this dairy cluster, there are about 30 dairy farms housing more than 30,000 cows. And we placed one upwind, as I mentioned, measuring a clean or a local background. And then we placed one or two instruments downwind, and it was either at site A, B, or C, depending on the forecasted winds. So as the winds traveled from the northwest, then our downwind instruments were able to pick up that enhancement of methane. And then we deployed these instruments during 4 seasons, in the spring, summer, and fall of 2019, and then in the winter of 2020. So we were interested in those seasonality patterns, and that's why we deployed it during these 4 seasons. So here's an example of what our measurements look like, and we quickly found out that these measurements were wind dependent, and there's a lot of day-to-day variability. Not one day is the same, and our methane enhancements range from 10 to 40 parts per billion. And you can see there's negative numbers. That means that the upwind became the downwind because the winds were actually from the south. So it just flips the equation. And so these arrows are pointing where the wind was coming from. They were coming from the south, and if you remember, there's tons of dairies to the southwest. So we were actually sensitive to those dairy farms instead of the cluster. So then for our research question, we wanted to isolate that dairy cluster, so we needed to filter our data to isolate these northwest winds so we can capture the dairy cluster. Okay, so in order to calculate emissions, which is a rate of how much methane is being produced per hour, then we needed to use a mass balance equation, which is very simple. It's an enhancement multiplied by the wind, the air column density, and then area of the dairy. So for us, we had a filtering criteria. We only used measurements that were during these northwest winds. We wanted wind speeds higher than 1 meters per second, because if you measure anything lower, then that's stagnant air, so methane can just accumulate and it's not representative of a mixed atmosphere. So we also selected the longest continuous periods where these meteorological conditions were favorable. So we weren't like picking a random point that had the northwest winds. We wanted actual periods where there was these ideal criteria. And then we also excluded days where we had influence from the southwest dairies. So for our results, we find that summer had the highest emissions, and that's consistent with higher temperatures, because during higher temperatures you have more bacteria activity, which drives higher methane production rates. Then we see lower fall emissions. That's consistent with lower volatile solid availability. So farmers in that cluster, they tend to clean out their manure lagoons during the summer or during the fall period, so you have less organics available for the bacteria to break down methane. So that was consistent with what we observed. And then in the winter, we expected to see smaller emissions, but we saw comparable to spring, and that matched observations from a previous study, and it may have been due to meteorological conditions. So these dairy farms, their manure lagoon sometimes gets agitated by precipitation or wind patterns, which releases methane bubbles to the atmosphere. So that's what we observed during the year 2019 to 2020. And then we also compared our results from the San Joaquin Valley to a study that had been done in Southern California and the Chino dairy farms. And comparing dairy cow had the methane emissions, then we calculated that dairy farms in the San Joaquin Valley, at least per cow, they emit 5 times more than dairy farms in Chino. And that has to do with the difference in manure management practice. In Southern California, they tend to use a dry manure management practice, which it involves drying out the manure rather than putting it into a lagoon. So there's less of that anaerobic conditions breaking down the organics. So for our objectives, we wanted to quantify methane emissions from a dairy cluster and improve emission estimates of dairy farms in the San Joaquin Valley. So for our conclusions, we observed a measurable methane enhancement from this cluster using the differential column measurement techniques, and we find that summer had the highest emissions, and the lowest were fall and spring. And then our comparison between the San Joaquin Valley and the Southern California dairy farms, we find that wet manure management practice emit significantly more than the dry manure management. So this can help inform farmers or any policies that need to be taken into place for reducing methane. Okay, so now let's get into our fire discussion, but I'm going to drink some water. Okay. So wildfires in California have become deadlier, destructive, and more frequent in the past few years, and particularly the year 2020 was a record-breaking year due to being the most fire active year with 9,917 reported incidents, burning 4.2 million acres, or about 4% of the state's land. And while wildfires is part of the natural ecosystem in the state, wildfire season has become prolonged, so starting earlier and ending later into the year. And besides wildfires threatening our homes and our forests, we're also concerned of wildfire emission smoke affecting our health. So we're often told to remain indoors during a wildfire event, as well as to purify our air indoors. And that has to do with particles that are released from burning. But smoke is a complex mixture of particles known as aerosols and gases. And most of the composition of smoke is made up of CO2, carbon monoxide, and methane. And with California wildfires becoming more widespread and severe, tracking emissions will become increasingly important in the context of carbon neutrality and air pollution impacts. So in order to calculate emission from wildfires, we need several pieces of information. That involves knowing the area that was burnt, the type of biomass that was burnt, as well as an emission factor from species of interest with respect to CO2. So that really comes down to the emission ratio, denoted as ER. And the emission ratio is often calculated from aircraft. So aircraft during a wildfire event flies through a fresh smoke plume, and then also measures outside the smoke plume. So it can calculate this enhancement of CO with respect to CO2. But aircraft can be costly and complex to deploy, and recently satellites have been able to make these calculations, but satellites do lack the spatial and temporal coverage to calculate emission ratios at a necessary temporal resolution. So an example is a satellite can take 16 days to cover the same spot. So if your wildfire is burning for 2 weeks, you might miss the event. So we proposed in my research that perhaps these ground-based remote sensing instruments can be used as an alternate technique to understand and measure these regional scale fire emissions. So in the previous section, I talked about the EM27, and it's similar to a satellite, so it measures the entire column of air from the surface to the top of the atmosphere. And what was exciting was that a detector was recently installed to measure carbon monoxide. So then during a fire or during combustion, CO is also released. So then we can calculate these emission ratios of CO compared with respect to CO2. So the measurements took place in the San Joaquin Valley from September 6th to October 22nd of the year 2020. So this was actually a study that I did by accident. So we remember during the pandemic year, we were all told to go home and stay there. But I got sad and lonely in Riverside, so I wanted to come back home, and I brought with me the instrument and I placed it in my backyard. I was actually interested in measuring the transition of fall to winter of dairy farms, and I was going to place it in Exeter, the backyard, and see what happened. But during this time, wildfires were burning all over the state, and I accidentally collected 2 large fires. The Castle Fire, which was about 40 miles away, and then we have the Creek Fire, which was about 70 miles north. And they had recently started when I got to the valley. So I was measuring plumes from these 2 fires, as well as mixed air from other fires burning in the state. If you remember, Northern California was also on fire, and the San Joaquin Valley was just engulfed in smoke. And we also know that there's dairy farms to the west and to the south, so I was also sensitive to methane and CO2 emissions from these dairy farms. So it becomes a very complex but rich data set when we have so many sources releasing greenhouse gases at the same time. So here I'm showing the time series of the first week of observations that took place from September 6th to the 12th, and we can see here, each of these panels is for one day, so September 6th through the 12th, and then we have CO in red, CO2 in yellow, and then methane in blue. And if you remember, I mentioned that CO is a tracer for combustion. So when something burns, even combustion from a vehicle, it releases CO. So if we're in a huge megacity like Los Angeles, you're able to measure CO, but that's mainly due to millions of vehicles driving at the same time. But if you're in a rural area like Portersville or Visalia, measuring in the fields, then most likely your CO is from a burning source like a wildfire. So we see these peaks of CO most likely due to fire smoke plumes transient over the instrument. And we also see peaks in methane, and most likely due to dairy farms. So we don't see peaks of methane at the same time of CO because dairy farms aren't expected to emit CO. And then in CO2, we see the same peaks of CO, and then we see the same peaks that methane had here because dairy farms also emit CO2. Let's see. So if we look at the time series of CO, we can see that the concentrations range from about 100 to 200, but on September 12th, they just skyrocket about 10 times higher than the local background. So we look at satellite imagery of what was going on that day. There was a huge plume coming from the Sierra Nevada, traversing over into the valley, and we just happened to be underneath it, measuring it. So it CO increased by 10 times due to that smoke plume. And if we take a look at CHAP satellite of what it was measuring CO from space, that satellite also captured this plume. You can see the same shape here. And if we plot the points of that satellite onto our data set, we can see that they line up really well. So as I mentioned, this instrument, the solar spectrometer, is similar to a satellite but measuring from the ground. So we can do a one-to-one comparison, and we compare CHAP, the satellite, to our instrument, the EM27 Sun, and you can see how closely the data follows each other. So we plot the satellite against our instrument, and we get really close alignment there with R squared close to 1, which is really crazy in science because science never works out for you in the atmosphere, at least. So this was something cool that we were able to do with our measurements. But also, going back to emission factors, then we're able to calculate the emission ratio of CO to CO2, which is basically just the slope of this scatter plot. And then we're also able to calculate for CO and methane with relation to CO2, and as well as modified combustion efficiency. So that gives you information of what the wildfire is doing. Is it flaring? Is it smoldering? How efficient is it burning? So the reason why remote sensing is so unique is that you can measure from a distance afar. You don't have to fly an aircraft above it. It's not dangerous. You don't have to be near the wildfire. So having this type of calculations from a remote sensing instrument is a new step towards gathering more emission ratios so we can better calculate wildfire emissions. So comparing our numbers to the literature, we have we plotted our emission factors with modified combustion efficiency in this plot. So right now, just pay attention to lower MCE, or the modified combustion efficiency. Lower numbers means that the fire was smoldering or burning less efficient. So you expect more methane and CO to be emitted. So this is going back to your basic chemistry classes of how combustion works. And then higher numbers means that the fire is flaming and burning more efficiently, so you expect less methane and CO. So where our measurement was right in the middle, and in this sweet spot, it means that the fire was doing both. It was both a smoldering and flaming conditions, and remote sensing measures an entire area. So these wildfires are huge. So you can have a fire behaving in different ways if you're measuring remotely. So placing it in this plot, it follows the same trend as other studies. So this just proves that our values are consistent with other studies and that this measurement technique is reliable and can be used in future studies. And just gathering all our data from previous years. So we remember the last topic of methane we measured in 2019, but we also had some data from 2018 in September. So we plotted everything together and to see any patterns. So in blue and green are the 2018 and 2019 measurements. And then in gray are all the measurements from 2020. And you can see these different patterns that become obvious. And extracting our fire smoke plumes, it follows this red line. So we can see that dairy farms don't really emit. From dairy farms, you expect more methane rather than fire smoke plumes, you expect less methane. So with this relationship and these different slopes, then we can calculate how much methane was emitted from wildfires. And this is important because we want to reduce greenhouse gases, we want to reduce specifically methane, but when a biogenic source is just burning and producing methane, then it's like it sort of counteracts our efforts. So comparing our calculated methane from wildfires, just the top 20 wildfires of the year 2020, and compare it to the anthropogenic emissions. Anthropogenic means caused by humans. We can see that this amount of methane produced by the wildfires is actually comparable and on the scale of human cost emissions. So not as big as agriculture or recycling and waste, but larger than commercial and residential electric power and transportation. So this just tells us that we need to figure out how to manage our wildfires, perhaps more prescribed burning. We need to reduce this burning and not have as many large-scale wildfire events like we did in 2020. So in conclusion, our objective was to measure greenhouse gases and air pollutants from California wildfires, and we were able to isolate a large fire plume to understand their fuel properties. So we find strong agreement with our ground-based instrument and the satellite, and then our calculated emission factors and modified combustion efficiency were consistent with other studies, which indicates to us that this measurement technique can be used in further studies. And then we measured a significant amount of methane from these large wildfires that took place in California. Okay, so now let's talk about what I do now as a scientist. I focus on mitigating methane using remote sensing observations. So remote sensing means that you're measuring something from afar, not directly. And some examples are the ground-based instrument that I talked about in the previous two topics. Another example is the satellite and aircraft. So in the early 2010s, mid-2010s, new technology for methane, had advanced for methane. And this demonstrated that the hyperspectral imagers were able to detect sources of methane. And an example is AVERS NG. It was developed at the NASA Jet Propulsion Lab. And this instrument was placed on an aircraft. And you can see what the satellite imagery looks like. So it seems like it's pipelines. And as the instrument was flying over this area, it was able to pick up an image of plumes of methane. So this was really exciting because it was at a high spatial resolution at a scale of less than 3 meters. And you can get quick data access, retrieve these plume images within hours. So the state became really excited about this, and they, along with the California Energy Commission, they conducted several airborne research studies. The first one was California Methane Survey that took place in 2016. So they flew over the state for several months, and they surveyed over 272 1,000 facilities and components, and they revisited multiple times to see if there was persistence. So in this map, you can see that the areas that were flown in 2016 in blue and then 2017 in green. So it was all over the state, in Los Angeles, mainly targeting landfills as well as Northern California, and then Bakersfield, we know there's a lot of oil and gas production. You're driving down the 65, you see oil wells. Okay, so what they found was that plumes were found in all sectors. Where you looked, you found. So then, as a follow-up study, there were the mitigation studies of 2020, 2021, and 2023. So this became more of taking action, and now the operators were notified of leaks. So for this, I participated in 2013. So we asked operators to voluntarily inspect and provide feedback on what was leaking and why. And this is a map of where the aircraft flew, Northern California and Southern California, mainly looking at landfills, and then in the center, or South San Joaquin Valley, looking at the oil and gas production areas. So here's an example of how plume mapping is used for mitigation. This is an example of oil and gas. And just looking at the satellite imagery, there's nothing there, but on June 12th, as the aircraft flew, it picked up a plume image. So there was definitely a bright spot indicated there was a leak, and then 2 days later, June 14, picked up another plume. So observed on the 12th, 4th, and 14th, and then the operator was notified on the 16th. So the operator immediately took action within 4 days. They conducted an inspection, they repaired it, and they let us know that what was causing the leak was fugitive emissions from a pipeline. So even though we don't see anything there, there was a pipeline leaking. So this technology makes the invisible visible, and we can now fix leaks. We can notify and work together with operators. And then after they conducted the inspection and repair, 9 days later, we received that response. So operators are willing to work with us and help us learn why these leaks are happening. So the overall results for the mitigation flight campaigns that took place in 2020, 2021, and 2023, we found that over 502 methane plumes were detected that resulted in 245 notifications with 75 different operators from 2 primary sectors, landfills and oil and gas. So communicating with these operators, notifying they have a leak, there was a response rate of 94%, which is really great. Operators are willing to work with us. And there was average time between detecting it and their response was 14 days. So there's quick action there. And based on operators' responses, the sources of methane were classified. In this pie chart, we can see that 40% were due to unintentional leaks. That means the operator didn't know they were happening, but they were able to be stopped and repaired. And then we have temporary activity at 27%, which means these leaks were due to construction or maintenance, and we don't expect them to be a long-term leak. And then just 15% were not found. That could be due to either persistent sources where it's not consistently emitting. It could be just like one day it does, one day it doesn't, based on different behavior. And then at 12%, we have process emissions. That means it's an allowable event as part of the process of how the infrastructure operates. And then at 6%, we did not receive a response, but that's very low. We got 94% response rate, which was really great. So going from airborne studies to satellites, that's our future, because with airplanes, you can only do it once a year. It's very expensive. They're great for pilot studies, to do research, but not really for sustained monitoring. So satellites will be needed where you consistently monitor. And 2 satellites will be launched in 2024, funded by philanthropists through the Carbon Mapper and Planet Labs coalition. And the state agency, CARB, will be receiving some data for free so we can communicate with operators. And then the state has also allocated $100 million to purchase additional satellite data so we can continue to do this mitigation. And that'll be awarded through a competitive request for proposal, through a proposal process. So that is the end of my talk, and thank you so much for listening. I will take any questions, and I hope you enjoyed it and learned something new about methane. So thank you so much.
I have a mic here. If you have a question, I'll come around with it.
So, as neither a dairy farmer nor a government scientist, hearing you mention the methane emissions from dry manure management versus wet makes me wonder, do you have any idea what drives the local preference for wet manure management?
I think it's efficiency. In the San Joaquin Valley, there's dairy farmers with thousands of dairy cows. So it's just more efficient to wash these feedlots versus drying it out within the feedlot and using a tractor or something, or a person to dig it out. So it's more efficient, especially in the industrial scale dairy farm.
Going on from his question, it may be more efficient, but isn't it true that methane also causes deaths?
Deaths?
Yes.
So,
And I just wonder how, in the vicinity of those dairy farms, what the death ratio is and what the illnesses are that cause these deaths from methane. I suspect that it has a lot to do with respiratory issues.
So methane itself, at a high concentration, can be explosive. But in terms of deaths, I think there's other air pollutants that may be more harmful to human health. For example, ammonia, that is a precursor to aerosols. So there's more things that get emitted that might be more important than methane for negative effects on humans. But in terms of methane, at a high concentration, can be dangerous.
Questions?
Any easy questions?
I had a question about a term, enteric, when we're
Enteric.
talking about the source inside the cow.
Mhm.
I'm not sure what that means.
So enteric fermentation is what happens inside
Oh.
the cow. Yeah.
I was just curious, you were talking about, you're collecting data about California, which I think is obviously relevant with the state. But is there global information? Because I mean, what we do in California doesn't necessarily proportionately impact the world. So do we know what's occurring in other countries or globally, and what proportion of these emissions are coming from California or coming from the United States?
Yeah. So California does tend to be a leader in environmental issues and how to handle them. So currently, there's very few places. Colorado is also doing these type of studies, but our goal is to create a framework where we can share with other states, other nations, that they can take and use using these remote sensing observations in order to mitigate methane. But yeah, the U.S. is a contributor to methane. I don't know off the top of my head the percentage, but it does emit significantly.
So I guess I just had like a chemistry question about You said that methane stays in the atmosphere, I guess, 10 years.
Mhm.
And so what happens to the methane? Is it just
So methane breaks down through chemical reactions, but it takes 10 years in order for that to happen. After 10 years, new methane is always coming out from different sources. So we do see a sort of constant concentration of methane across time, but it is increasing. So these concentrations are slowly ticking up, but it's through chemical reactions that methane breaks down.
Have you heard of a regenerative farming?
I have, yeah. I think it's a good practice, but we need to have more exposure and in order for people to learn about it and choose what type of farming they want to do. But definitely a great idea. Is anyone interested in environmental sciences, environmental issues?
I wanted to ask how the detectors work. How the detectors work? Does it like watch the fumes?
So the detectors, they use light as the source. It could be through the sun or some sort of laser. And there's different types of techniques. Some of it does use a vacuum to suck in the air into a cavity where there's a laser with a mirror moving back and forth that extends the path, which makes it very, you can measure it at a low detection limit. So there's different techniques. For the ground-based solar spectrometer, it just uses the sun, and anything along the path between the surface and the top of the atmosphere can be measured. So it just really depends on that. And it's a great question. For example, if you're interested in optics, engineering, all that, like we always need improvement and new development of these type of instrumentation. So it's a really interesting question.
Feedback on that, is that the same way they kind of analyze gases on like exoplanets and things to see what they're made up of?
Yeah, so solar or spectroscopy, it's widely used and including in other planets. So during one of my summer internships at the NASA Jet Propulsion Lab, we were studying hydrated clay minerals that were analogs to Mars, and we were using a spectroscopy instrument to study those minerals, and it was in the same way that they were going to be measured for Mars. So yeah, it's a widely used technique. Any other questions?
If you have any specific additional questions, you can always come up after you're here.
Yeah.
But I think, are there any other questions? Okay. All right. Well, thank you very much. I will have these tickets for anyone who needs them. And unless you have any other questions, we'll open the door and thank you very much.
Yeah,
Come.
thank you. Thank you for coming.